I'm going to present our work on using data types as an encoding for grammar-guided genetic programming. This is work done with a few of my students at LASIGE. So for those of you who don't know genetic programming, it is an heuristic method for complex problems that tries to find good enough. There's no guarantees that it will find an optimal solution, just like random search wouldn't have, at least in reasonable time. Now you'll see here a few areas where it has been used. So climate prediction, mechatronics, diabetes drug discovery, financial forecasting, and on the other side, topics more close to our community, such as software fault prediction, test case generation, automatic optimization of GPU code, designing neural networks, and even designing levels for computer games. Now you'll see that these two lists are a little bit different. So you'll see that the users on one side are experts in their domain, but they're usually novice programmers. They might be experienced, but just for their goals. While on the other hand, software engineers are used to working on larger code bases, modularity, maintainability. Those are concerns for their kinds of projects. While these domain experts, they're just doing one experiment, they want to try this, maybe run this for a couple of days, see if it works or not, and just throw away this prototype until they find something that they want, and then they can just use that solution and not care about this infrastructure. Second thing you might also need to know is how genetic programming works. So the user just needs to define a search space. So these are all the parameters that can change in the solution, and the fitness function that tells for a particular candidate how good that solution is, right? Ideally, gradually. And internally, the infrastructure will generate a population of programs from this search space definition. So these are trees, just programs, and as you see, there is no parsing. This will be relevant in a moment. And these trees are only generated within the search space defined. Then using the fitness function, we are going to select the best out of all of these random trees that we then combine together, take parts from one, part from the other. And then we can even mutate them, take one of these trees and change just a little bit. And out of this, we'll have a new population, hopefully with better performing trees. And then we repeat this until we're happy or time runs out. Now, this work focuses on designing the search space. You can use types or you can use grammars. Usually for more complex domains, people tend to use grammars. And you'll see a very simple example, but you already noticed that there's an X colon IDX. So that's a little bit of Python that appears here, because when practitioners use this, they're actually designing a subset of the host language. So they don't want to write interpreters. So they're actually encoding a subset of the target language. Okay, and this is also important for this work. Now, a more complex example you'll see here also has the same problem of targeting Python, and you can also see how floating point numbers are just two digits on each side of the dot, and you'll see also the NumPy functions available here. And you'll see a lot of repetition, because this is actually giving more weight to some productions than the other by simply repeating them. This can also be improved using probabilistic grammars. Another real-world example. Now you have statements. You also have assignments, and you have for loops, which are just a complete mess, because what you see here doesn't correspond to the code you're seeing. There's a lot of substitutions going on and syntax changing that's going to be replaced with other things. So this is not the kinds of grammars you'll see typically when writing a parser. Still, it's the one that restricts the problem to the relevant solutions. Again, limited by the target language. A final solution, this one has also has for loops and statements and mutation, and you can see the by number of components on this one. This is not that easy to design this grammar, and one of the reasons that when you write this, you kind of have to run it to see what kind of programs come out, and you might have some errors like these nested loops that only appears after a couple of hours. So you're kind of designing your grammar, you're leaving it running for the night, and in the morning, instead of finding a solution, you find that it crashed because a given solution was not valid. Okay, and this can actually hurt the performance of your program. So we identified these challenges. There's a lack of knowledge and experience in designing grammars for these practitioners. They have never heard of BNF, extended BNF, or similar languages. They have a big confusion between the syntax of the language they're working on and the language they want to target. So they are kind of having two languages in the same program, and it's difficult to read and understand the effects of one on the other. Especially because of this dissonance between dealing with characters that are replaced and expanded and the semantic language. For instance, that your program needs type check, it has given indentation or a parenthesis needs, which, well, if CS students have difficulties with that, can imagine people with other backgrounds. And in practice, there are no tools for this. So when they design this, they just have the support for BNF, which is almost none. They don't have support for the target language while they're designing their grammars. And this is the main problem in practice. So our approach is actually to not use grammars for the user, we use it internally, but rather we propose to use data types. So one of the reasons that strongly typed GP, so using types, is already very popular and available in these languages, but is restricted to ints, floats, and very simple data types. Developers also want to use a single language for everything. They don't want to have a language for describing another language, and they want all the tools to be the same. They want autocomplete and type checking. And as we'll see in a moment, these two can be equivalent. There are a few concerns regarding that. So we start with a simple grammar, and to show our encoding, we have here our implementation in which you have, for each non-terminal, there's an abstract class. For each production of that non-terminal, there's a concrete class in which each non-terminal that appears is a field with the type annotation. These productions can have names, not very common in BNF, and the focus is on the structure of the program, not the syntax itself. Well, we have that using the string representation, but that's just one of the possible semantics. In practice, people will have simulations, evaluating data sets, doing SQL queries. You can have any kind of semantics in these nodes. While in BNF, you either have these loose as functions, and you need to correspond your syntax with the right syntax. And if you want types, you have to encode types in the grammar yourself. And types have been very helpful in finding these subtle bugs, especially when you generate very complex programs with a lot of combinations. This is a more realistic example in which this is an average, just like an SQL aggregation. And you just have 3 fields, so 3 parameters for this particular block, but you have a huge bunch of code for the semantics. And in this case, it does these aggregations, takes care of corner cases in the dataset, and so on. But the idea is that the user can write these basic blocks for the language and just use inheritance to say how they can go together and use fields to use them. And we also propose METAHANDLERS which using the notated type notation in Python and the concept of refined types, we can say that this integer is between 0 and 200. So whenever we generate a random age, we actually make it between that range. When you do mutation or crossover, the same thing. And we can have these meta-handlers for many things, including generating values based on other values or changing probabilities. Speaking of probabilities, we also support probabilistic grammars by saying that this class container is 3 times more probable than all the other nodes in any choice. So our approach was evaluated in 3 areas. So first, expressive power. So we encode exactly BNF, but we also have some extended BNF features that we can support using the optional and maybe types, and the list between size meta-handler for lists and repeated symbols in extended BNF. We also support probabilistic grammars. We've seen that using the curators. And more technically, our meta-handlers are equivalent to L-attribute grammars. So those are grammars with semantics that are evaluated always left to right. So there's an order in which all the attributes that you can access are already filled in. So this also corresponds to dependent types. So in terms of performance, the second vector we evaluate is on. This is the running time of the same conditions of the simulation, and you can see sometimes it's faster, sometimes it's roughly the same. So our main conclusion is that it's on par, and this is what we want. So we didn't want our solution to perform much worse, to have disadvantages. It's on par. Usually the optimizations come more on the user side, on the semantics of each operator. It's not that affected by the framework itself. And the third and most important vector is ergonomics. So for this, we evaluated using Keeper's framework, in which we evaluated these 2 approaches using granularity, coherence, and harmony. So regarding granularity, when we have feedback about a part of your program, in our approach, you can directly say if it's part of the semantics, it's a problem in the class, or in the abstract class. So you can see what part of the grammar the problem is in. While in BNF, if the BNF syntax is okay, you don't know if the actual problem will be okay or not. So there's a mismatch also in the granularity of where you find the problems. And regarding coherence, in BNF, everything is strings, so there's not a lot of coherence there. While in our encoding, there's this hierarchy of concepts in which you can have the language blocks are classes, their semantics are methods, and you can put blocks that are related together in modules, and you can have this hierarchy in which there's a coherence in each building block. So each class only concerns the semantics of itself. And the final criteria is harmony, and this is where we see this mismatch between BNF language and the final program, where there's no direct correspondence from the final program to the original language. But in our encoding, if you see something in the final solution, you'll see exactly what it is represented in the source code of the data structure. So it's more harmonious. And to conclude, we have extra information. Our framework, which implements this approach, is available in Genetic Engine. You can try it out. And it also has been used to improve explainability in bike usage prediction, credit classification. You can read more of that in Leon's thesis. But the idea is that making these concepts more independent allows you to increase the readability of the solution and not just generate NumPy-like code in your grammars. Thank you.
Okay, so I think Alcides can hear us. So if you have question, then you can speak and Alice can type fast. Are there any questions? Okay, I'll bring a microphone.
Otherwise, here. So maybe he can't hear.
And let's see.
Do you hear?
Can you hear us? Okay, good.
Okay. So one question is that there are a few things in work, and can you compare or concisely compare your work with existing work? And I'm not the expert, but there was a discussion among reviewers that you should compare your work with Poly-G, and so on. So could you say something about that? Right. Did you understand my question? It's constant.
Just to double check the question, the attendant who wants to know more about how it relates with past work, such as Poly-GE, is that right? He's double check your question. How it relates with past work, such as Poly-GE? Yes, that's correct. So the internal mechanism is the same. The difference is the user language. Poly-GE uses BNF. We support this data type encoding. Which has made non-CS users much more productive. Yeah, this is the end of the answer. Do you have a further question? Any other questions? So it's on the language integration with the target language, which is Python, more than the performance. That the answer makes sense. Any other questions? Okay. In the interest of time, thank you for the question.